All right, welcome everyone. Let's try this again. So I've been working on this little programming language called Macha. And Macha is essentially a scripted version of like Rust syntaxy, statically, like it's precompiled, so it's like it's a bytecode language. It has only a stack, it doesn't have registers, but it does index the stack, so stack indexed, I guess, or like stack plus offset, however you want to call it. And it's pretty fast. It's statically typed, and it doesn't have a lot of features yet. But it's going to essentially work as a scripting language for Rust. So let's say you want to write some Rust code, and you're like, oh, I would really like users to be able to change the behavior of this, and I don't want to have them specify everything in TOML, and I don't want to have to embed a JavaScript interpreter or a Lua runtime or whatever, and I also don't trust people to write code, like native code. So I just want like a super isolated, simple, fast language that feels like Rust, so I don't have to context switch too hard on the syntax. And I just want it to kind of work. And it's quite lightweight. So the dependencies right now of cargo tree Macha. Macha itself has a couple dependencies. The direct dependencies is SHA-1 small, which is not actually required. I should probably make that optional. Strum for a little bit of like, this is just for the decompiler because it contains a decompiler. And this error for errors because I can't be bothered. And then of course UX for some differently sized integers, but I might get rid of that. So not a lot of stuff here. And then it also has about 5,200 lines. The interpreter is just glue code, and the compiler is also just glue code. They're like 100 and 200 lines each or something. They're just glue code. They don't really matter. They're mostly shit. But yeah, it's about 5,200 lines of Rust because it's a handwritten lexer. Let me just show you really quick here. So it's a handwritten lexer that, oh, well, there's some dead code here. All right. It essentially tokenizes all by hand and unit tested, of course, a little bit at least. It does then generate an AST. And I can actually show you these. Let me just show you these. So I'm going to go into our tests here because there's a couple tests in here. Let's just write our own, actually. I don't want to deal with this. So hello.mch, and mch is the extension that I've came up with for this. I know it's kind of taken by like Minecraft or something, but I don't really give a fuck. So let's do this. So cargo run pmachi. So of course this is all going to be changed later, like the way the interpreter works and stuff. It's just kind of for testing right now, right? So we're going to go hello.mch, and there we go. And so what you can see is that it'll run something. So it'll like compile the AST, then it has something called AST2, which is sort of like a second stage AST. It then runs it. So it first does a like compilation step. So like this is still part of the compiler. It's a little confusing here with the Macha because it's just a shit program I wrote for fun to like just quickly call different functions of the Macha library. So Macha is a library, Rust library with very few dependencies, as you've seen, and so now we just want to call into that. And here we see that there's some opcodes, there's some allocation going on. Pretty fun. But let me show you this. So what you can do is you can compile it, right? So this is just the compiler, and the compiler can output some other code. So let's run the help here. So we have print AST and exit, which is actually quite helpful. So let's do that. So the AST for this is now this. So let's write some code. So 1 plus 2, and then we'll do 5 plus 6 times 8. Okay, so this is this is interesting. So, and then let's have y be 2.5 f and y minus equals 1.0 f. Okay, so pretty simple. And then we can have some loops later. Or we can have like an if y is, or if x is 0, x y is 0 or something, like some stupid fucking code. We don't care, right? Does not have to make sense. And there's no print, there's no functions right now, but we can just see it. So this is essentially what it compiles to first, right? So first, well, the very first thing is it tokenizes it, but nobody gives a fuck. Tokenization is very, very like boring, right? Like usually you would have your library do that. So we don't show that, but we have essentially an AST, and an AST is just a tree of like the program. In sort of, you have to imagine it like the compiler would walk as deep into the tree, so depth first, and then walk back out and generate the code that way. So it has to do with precedence rules, like what happens first and stuff like that. So you'll see, for example, that the first thing that happens is that, well, this is a little hard to read, so that's why we have AST2. So AST2 is sort of a more refined version of that initial syntax tree. AST stands for abstract syntax tree, right? So, but anyways, we have the second one here, where we see there's a declaration of the variable x, and there's an add instruction with the int 1 and the int 2. And again, you see there's ints here, over here there's floats, so it's statically typed. These look like they're not, like this looks kind of like JavaScript or something, but it isn't. These are statically typed. So if I do x is 2.5, then it will complain. Might complain later. Yeah, it complains later. Complains later in the compilation step. Yeah, there it is. So right now it's just an assertion. Type mismatch failed because it expected an int, but it got a float. But that's not very pretty right now. But just so you know that it's statically typed. And I'll get to the meat of this video in a second. But essentially, this is what it looks like. So we have an assignment with first a multiplication, then an addition, stuff like that. And it's an assign mul. So you can see that the assignment of like this essentially generates this code. It generates the same as this, right? So, and then, this, of course. So that's what that generates. And it makes a lot of sense if you know programming, right? So very simple. It generates if, then else stuff. And the other thing this does is it can generate, oh, I fucked something up. Where is it? I don't know. I'm going to get rid of the, oh, it's because this is not a float technically. These are just quirks with the parser. It doesn't really matter. Okay. So what we can do is we can give it the -s flag. So regardless of whether I give it the -s flag or not, it dumps me a file called hello.mcb, and that's the binary file essentially. And as you can see, it starts with Macha, and then it has some header information, and then it has the code. So very simple. And if you now look at the hello.mca, which is generated by the -s flag of the compiler, you see that we now get some. Let me just actually open it here in the editor so you can see some syntax highlighting. So this is assembly. And this is essentially our code decompiled, like so compiled into bytecode, and then the bytecode is decompiled. So this has no information about the actual program. This only has the bytecode information. So here you can see the actual bytecode and the way that it is sort of rendered into the file. And this is why we need the SHA-1. It's just so that we have like some sort of reference for whether something changed, even though the code doesn't change, stuff like that. This is for unit for integration tests and other tests. It's just like, if the SHA changes, then we fucked up something. So same with the version. That's the bytecode version. Bytecode versions differ. And yeah, so we have constant tables here for the constants for the floats. So you see the CF because it floats. And this is just because floats are 64-bit and we don't want to store them as immediates. Yeah, technicality. We allocate 6 variables because we allocate space for 6 variables because at one point we will need the 5th index for some multiplication, right? And that's really the only reason we have 6 variables here. So we allocate 6 spaces. We have some load instructions, the addition, some more load instruction, multiplication, addition, multiplication. Here we load the constants. Here's a jump if not equal for integers. So you see all these are typed. So this is an F instruction, a float instruction, this is an integer instruction, stuff like that. And at the end, we have a halt. And this runs quite fast if we compare it to other languages, which we will. We have a thing that counts to 10 million right here. It's essentially just a benchmark that counts to 10 million. And don't worry about the recording breaking this because this is running on a server. So this is not where the recording is happening. And you can see that we are about as fast as Lua with this example right here. And there's still some old code in here, which we don't care about. And if we run the 100 million counting step, I'll show this better in a second, just trust me on this. It generates markdown files with the results, so we don't have to like actually analyze what this says. But currently the Macha interpreter is about as fast as the Lua interpreter for what we can do in Macha, which is quite the achievement if you've seen the Lua interpreter. So Lua JIT is of course much faster because it's JITted. Same with Dino, no, they're all JITted, right? So they don't really count as much. But you can see that like here by the times we have 450 milliseconds for Lua and 490 milliseconds for Macha. And this varies greatly depending on at which point of the development I am, because sometimes I add some optimizations and then I add some other stuff and it, speeds it up, slows it down. This includes, of course, the compilation time, right? So stuff like that. Anyways, so now that I've sort of explained what's up with Macha and what it is and what it can do, because this is just about everything it can do. I mean, it can do a couple more things. We can look at like the expression test here. The expressions from hell. Where is it? Where's the expression from hell? There it is. So this is essentially as much as you can do right now. So, well, this doesn't test floats, but like other than floats, this does everything that you could possibly want. It does. There's short circuit evaluation, for example. Let me actually show you. This is really interesting. I hope I'm not like wasting too much time here and losing everyone, but I think it's quite fun. So tests code AST2 expression variable used before declaration. Oh, I think there's still like a bug in this particular example, because this example is only for the AST generation. So I can't show that right now. Let me show it in the example here. So if I do let's declare two variables, A and B, and we say if A is B and B is 2, then I don't know, let C be 6 or something, right? Doesn't really matter. So now we compile this, and it actually is really interesting what it does. I don't want to like toot my own horn too much, but it is quite interesting. So if you look at the assembly generated, this generates jump instructions, right? So the first jump instruction is obviously the I can actually overlay this if we want. So that's this, and then that's this, right? That makes sense. So let's load 2. And then this is the, well, I can't really overlay because it's too complicated, but like the if is essentially this. And so it essentially generates like, a comparison between these two. And if that's not true, we just jump to the end of the if right here, because we don't even need to check the second one. So it does short circuit evaluation is essentially all I wanted to say. There's a couple things. It's quite fun. My cat just jumped on the table. I hope you didn't hear that. Probably went like, it's a fat ass. Love you. Okay. So what I want to do is add functions, and I figured I might as well just record this. Don't throw the pen out on the ground. My kitty's throwing the pen on the ground. Okay. Still recording, right? Fantastic. 14 minutes of rambling. I love yapping. Okay, so let's figure out how we can do that. So I have this, where is it? It's in the parser here. So this is a function declaration. So you can see it looks like Rust, and it's statically typed, and we don't care about the types right now. We just care that they're there. So we have a function called hello world that takes an int and a string, yeah, whatever that type is, we don't care. and returns some object of type no yeah, and then returns 42. So we test a couple things: the function keyword, the return keyword, the arrow operator, the that sort of thing. And this test, all this test does is it lexes it, and then it parses it, and it just checks that that does something. Like we don't really care about anything else. We just want it to do something. Right? So I think I changed something somewhere. Let's do that. What did I change? Lexer expect. Oh my god, it's the code that I deleted. I don't know if this was this recording session or the previous one, but I essentially deleted this code thinking it wasn't used. Okay, so so this always fails because I haven't fixed that test yet, but I don't care. So we expected a left curly, but we found a right parentheses. So something's going on here where essentially I've started implementing function parsing, but there's a lot more to it than parsing. And I'm actually gonna draw this in Krita. Sorry about the flashbang. Let me color this entire place a darker color. Okay, so the idea is that we have a bytecode file, right? And this, bytecode format, sorry. And the way this bytecode format works is that we have a header. Let me just find how to not fill. How can I not fill? I don't want to fill this. Why am I always using shit? Not filled. Outline brush. Good enough. Okay, so we have our file, and our file is a bytecode file, and it starts with the word Macha, right? So that's up here. So this is the header Macha. Okay, and then we have some other information we don't care about right now. Okay, so that's our header, right? And then we have, in maybe a different color, we start having some things here. So first thing we have is constants, right? So we have our constants right here, and it's multiple tables. So you have your floats, you have your string constants, which by the way are supported, just not in the bytecode, and then your int constants. Okay, so these are your things. So oh my god, why did I choose this thing? This is kind of atrocious. 12, good enough. No. Dude, how small do I have to make this text for it to fit? Okay, it doesn't go smaller. Okay, well, it doesn't matter. So these are our floats. These are our floats. These are our ints, and these are our strings. Whoops. And they are constants. Okay, so these are constants, and that means that these are essentially, they have to be hard coded in here, and we don't really care too much about them. Then next thing is we need to have functions. Okay, so this is not implemented yet, but this is what we need. We need a functions thing, make it quite big. We'll get to that in a second. And then we have code. And so the code segment is kind of the biggest segment. It's got all the code in it, okay, all the bad code. So let's write this. This is functions, not a vector layer. This is functions, and this is code. Okay, and so in the functions, we want two types of functions, I reckon. And I'm just making this up on the spot because I really don't know yet. But I think we want internal and external functions. Okay, so we'll have internal and external functions. And the internal functions will be essentially pointers into the code. Hear me out. Hear me out. So we essentially have some sort of, like, this is a, let's make a single function here. So let's say that purple is a function. So this is a single function, okay? And the single function has an ID, right? And that corresponds to an address. My God, I cannot type or write or whatever with my mouse. Okay, so this corresponds to an address, and this address lives somewhere in here. So somewhere in here is a block of code that contains my actual function, okay? So these are internals, right? They're internal. And then these are external functions. And so external functions will be sort of weird. So right somewhere in the code, we have like call b. And then this b will actually point to this ID, right? that makes sense. So it'll say, call function number 2, and then it'll call function number 2. It looks up the address of the function. And the reason we don't do like call with address is because it's a little, well, we have 8 bytes, and depending on how far away the function is, so we might have like iCall and call, like immediate call, or like constant call or some shit, some sort of call instruction. Doesn't matter. The point is, we have external calls, and these external calls will have to be like name lookups, I think. So let's do that. So we have a name, and then we have an address. Well, actually it's blank. That's the point, right? It's blank. Whoops. Oh, that's cool. So this is blank. And we don't know what goes here yet, okay? Because this is sort of like in an ELF file, the linkable section, right? So these are external. And these are external because there will be calls in here to those. And I mean, they will be by name, but I think they also need an ID so that we can call them. So they have a name, which is used. So the name is used at link time. The ID is used by the call instructions, probably like some other external call instruction, whatever. It doesn't really matter. I don't want to have to resolve it. So I think we'll have to do like an external call instruction or something. And this just calls some sort of ID, right? Like, again, this is not that important right now. So we do a lookup through the ID of what address this is. And then this is the crux, right? This is going to come from somewhere else. So something else supplies this address. So either we attach a sort of fake segment at the end where we like load functions into, like from a different binary, right? So we take a different binary, like essentially like a linked, like a dynamic link step, right? So we essentially load a function from some other binary object. Or alternatively, the VM basically says, I got you, right? That's the VM saying, I got you. And because the VM says, I got you, we put some special value in here, like -2 or something. It doesn't matter, right? We put some shit in there. And what that means is essentially that the VM knows, okay, this is something I have to implement and is required, right? So in this way, the bytecode can say, okay, I just care about the print function and the whatever function, and you just give me those and I'll be happy, right? And then it's up to the VM to decide, okay, is this provided by the VM? Is it provided by another binary object? Is it provided by, I mean, it doesn't matter, right? That is the idea. And in optimization step, because we have to think about performance a lot here, an optimization step, and we'll look at the Lua source code in a second as well for the Lua VM, see how that works. But essentially, we just need to figure out, can we do a reverse lookup? Because this is slow. Okay, let's say we have a call. The call then has to look up, and then the lookup has to do some shit, and then lookup gets back to us with some address. And that does not spell it. I'm so sorry. Okay, let me switch back to something I can actually use. So the issue is we'll have the call instruction. It'll go like call XYZ, right? And then XYZ will be an address like that. Okay, and so now we somehow have to do this lookup. There it is. We have to somehow do this lookup. And then we have to jump to that address, right? So this is essentially a jump, not really, but it's a jump to the RX1234. And when we're done, I guess we also have to store the return value. I guess this is a jump plus store return value of in some way, we don't know how. And then we come back and we say, okay, now we ret to the return value. So we return to ret, and then we're done. And the way that it could work instead is that we have call like XYZ. Okay. So this is method 2. So this is method 1, the easy one, right? And this is method 2, the hopefully fast one, okay? And the hopefully fast one essentially just needs to figure out, like how do we, okay, so call XYZ would compile into some sort of, like there's a couple of bytes, right? Like, so that's exactly how many bytes it is. And then there's some sort of instruction. So this is the call instruction, right? So whatever it is. And then we have a couple bytes here that we can use. So how about instead of storing like the ID here, because this up here would store the ID. So this would be like some ID. So this would be like function 2. That's a lot of ACID space. So how about instead of doing this, the linker, which I'm just going to call a linker at this point, the linker figures out that this is actually a call to 1, 2, 3, 4, which means that this will be CA, and then it does not know. Okay. Whatever 1, 2, 3, 4 is like hex, right? So it's like, I don't know. Let's just pretend that's 1, 2, 3, 4. Oh, actually, no, it is hex, isn't it? Okay, this is hex. Okay, so we essentially replaced, and this can be more. We essentially replaced the call with a call into something else. And importantly, we could also, so the VM can keep track of this, right? So we don't need to care about that. The VM can keep track of it, like sort of opaquely, we don't care. But we need to essentially go through the binary, find every part where we have a call instruction followed by XYZ, or like whatever the ID is. And instead of leaving it as a call to the ID, we actually exchange it with an instruction that does a direct call to the address. That's idea number 2. The only issue with idea number 2 is that we do need to do a lookup. So let's do pros and cons. So pros and cons. So again here, so method 1, pros, cons. So pros, easy to implement, and lookup is, well, this is kind of the only thing is that it's easy-ish to implement. The cons is that it's slow because it has to look up stuff. Okay, then the pros of this one is that it's fast, because as ChatGPT suggested here, there are no lookups. However, and it is actually an O of n one time at startup, because yeah, so this is an O of n one time at the startup because we have to go through for code size n, right? So we have to go through every single instruction, check if it's a call instruction to an ID, and then replace it with the call to that ID at startup. So this is VM startup. And this will actually have to do the lookup every call, right? So, but this is O of m for m functions, okay? So if we have m functions, it has to do some sort of lookup, or O n m log m or even O of 1 for hash maps, right? So even if this is a hash map, which it probably should be, we have to build the hash map. We have to do hash map compares. Like, okay, it's not. Oh, it could be a look. Oh, it could just be. I think it's just O of 1, right? Because the IDs. So okay, never mind. So O of 1. So look up every call every time, right? So every time it's called, and versus do an O of n at startup for code size n, but then no lookups at runtime. And I think the only con to this, that's a con. The only con to this is that the startup time increases, but the startup time is so meaningless. It's like so meaningless that even in the smallest benchmarks, it does not make a difference at the moment. And the compiler is not optimized at all. Like it iterates so many times over so many things, it allocates, it does all sorts of things. All sorts of things. The compiler, right? Mind you, not the interpreter. The interpreter does not do that. And I think we'll have enough function call overhead due to having to allocate stack frames and like initialize stuff and things like that. So I think we'll have enough shit to worry about where we don't necessarily need to also burden ourselves with a lookup every single call. However, this is a link time. So this is link time, and this, I mean, also is link time, but this is purely link time, right? So this is actually something we can implement right now. And I mean, these are both link time actually. So this is something we can just build right now. And then later we can decide how the VM is going to deal with this. Just, some notes. So this is a link time notes MD. Okay. Now that we've yapped enough, let's see what we can do. So, how long have I yapped? An hour? 30 minutes only. Damn, I've been yapping fast. Jesus. I got through a lot more than I wanted to already. Okay, so function hello world. So this is failing. Now the question is, why is it failing? It's failing because lexical error at 250 expected one of left curly. So this is line 2, and 50 would be there. So right here it expects an opening curly. I think it's just because I didn't implement the whole thing fully yet. Yeah, so I started implementing functions, and then I kind of got busy with something else. So we'll just jump right in. So consume identifier as name. We're in the parser, so this turns a token stream into an AST. So we consume the left parentheses, and while there is no right parentheses, oh yeah, so we test for the right parentheses, but we don't consume it. That's probably why. So we need to actually consume the right parentheses. So the way that these work, as I said, is very unoptimized. Test any will test that some sort of amount of token types matches a single, like an expected set, right? So you say, okay, I want to write parentheses, then it will match on that. But you can also say I'm expecting an identifier that is fn. Or alternatively, you can say I'm expecting these three things in order. Not that we would, but so that should probably fix that test partially. Yeah, that fixed that test. Okay, fantastic. So now that test passes. Now let's see, I think in the code generator, we have a to-do. Yeah, there it is. So for both the reference and for the function declaration. So how about we now write a little test program for this. Let's write a little test program here called exec function decal.mch. Rust. So I'm using Rust highlighter because it is pretty much Rust. So hello world EP int return EP plus 1. So that's what we want to support, right? That's like the basics. So Macha, let's just run Macha immediately. So we'll just do tests code exec function decal, and it crashes with not yet implemented. But we do see the AST2, so we can already check if this makes sense. So we have a function declaration, and I've obviously built most of this off screen already, this parser, but this is literally the entire parser. Like there's nothing else for parsing the function. You just consume the function, consume the identifier, which just does like, you know, check that it's an identifier, match on it, grab the name, return the name. Consume unchecked, consumes the arrow, so we have the arrow operator. Let's see if it's right. We have a function called hello world, that's correct, with one argument that is yippee int. So the first thing is the, these are just strings at this point, right? Because they don't really, AST2 doesn't exist, right? So this is the original AST, which is the first AST, which is a bit dirty. But it essentially shows us that right here here we have the function declaration. And then right here we have the yippee int. So yippee type int. Return type is int, which is good. It figured out that there's an int return type. Then we have our body right here. That's correct. So if I control click on this, you can see that jumps to the right point, which is a block, which is correct. Then it finds a return statement, which is correct. Sorry, my cat jumped on the table again. And then we have the identifier yippee, and that's a primary expression with the operator add primary expression literal, which is correct. So it parsed it correctly. But then it ran into here and went, oh, I don't know what to do now. So essentially what this AST2 step is a simplification of the original AST. And the reason we have these two steps is really just because of legacy reasons, like, and it feels weird to say legacy, even though this code base is a couple weeks old, but essentially the original AST represents the fact that this is a recursive descent parser for the language, and it represents that grammar that I came up with, like specifically that grammar. So you can see this in the original, in the AST source code. You can see that this is it cannot be left recursive. And that's really important. So because the grammar cannot be left recursive, it becomes kind of complicated to do very simple things. And that makes the AST also more complicated unless we do some weird shit to it, which is what AST2 is. So gen AST2 generates a second AST version that is more, that is left recursive, essentially. And left recursive just means that, like, you can have an expression that resolves to another expression and something else. Whereas in the original here, you can see this should have another expression, but instead it has a primary expression with operator add instead of being an add expression with two operators, because otherwise it couldn't left recursively parse. It does not matter, you don't care. But that's kind of it. So now we need to see if we have a meta expression for the return statement and the function declaration. We do. So the return statement is an option box. Oh yeah, because you can type return without anything. Yeah, you can just type return, right? That makes sense. And then we have a name. It's been a week or 1.5 weeks since I looked at it, so I need to get familiar with that. This is the arguments, of course. So name type, return type option, and body box T, and T is the type of the expression, which is essentially, it's not the type of the expression in terms of like the type system. It's in our case, it's what we call a meta expression, which just associates an expression with source location so that we can have this source location information, which is really important for the error messages. So it's a little weird, but it works fine. Okay, so let's go into the AST2 and let's implement this. So this is actually fairly, well, very straightforward. And I think we can let the thing run, but we'll do. So condition expression, well, no, not a condition. It's called the body expression is going to be gen AST2. Yeah, that one. And then we just return a meta expression that is a expression function decal. And the source location is, does it not? Oh, do we not store the, I swear we do. Oh, there it is, ast.block.cloud. Yeah, I remember. It's a bit of a weird quirk, as I said. It's a little weird the way everything works here. But we have this, like we match on, because the AST itself is also a meta node. So it's a node, but it also has a source location. So it's an AST node with source location. And so we can do ast.node match on that. But then if we want the source location, we have to do ast.location in order to get the location of the entire expression, not like the location of the body. This seems like I'm just being weird, but trust me. Okay. And this is probably box new body expression. Sort of. Oh, okay. Why? What is function declaration? Name string, and this is name string. Oh, I need to clone these, I think. And return type. And args clone doesn't work because expected struct vec found option. Oh, option vec. Oh, interesting. It's an option vec in this. That doesn't really make sense. We don't need this to be an option because not having arguments is just an empty argument list. We don't need to have like you don't want to encode the fact that it's empty twice. You don't want to have to be like, oh, is it an option? Like, is there something in it? And then like, oh, what's in it? Oh, an empty vector. Like, what the fuck does that mean? So I'm gonna make sure we don't mess that up. And this probably broke the parser somewhere. Yep, there it is. Right, that was the easy, simple fix. Okay, I'm actually gonna make this a little smaller. So, see. Now just the return statement, I think. What does this? It have? It has the expression. So, oh, okay. So the return statement expression is going to have a so the return value is essentially again xpr to oh sorry ast2 for the expression, and then we just want to return that. So ak meta expression expr return statement, yeah, whatever you say, buddy. And this actually expects a, yeah, that makes sense. So if let some expression is expression, then this, otherwise, let's actually make it another sum none. And the fact that this doesn't work is like, oh, and this doesn't work because we have to, how do you do that? You do like, there's like this thing where you can map, oh yeah, that's the one, map box new. Thank you. Sometimes the Copilot thing is really useful. Okay, let's continue. Okay, fantastic. So now we have the AST2. And you can see there's a little bug with the source location here, but that's not a biggie. It's because this is a pseudo block. Because the program doesn't really have a block declaration here, but it technically counts as one big block because you can just put code here, right? Like that's code. So we have to put that somewhere. We put that in an imaginary block that's a 1.1 at an unknown file. It's a bit dirty. You don't have to necessarily do it like that, but yeah. Okay, so what do we got? We got function declaration hello world up_int. Return type is an int, and then the body is a block with a return statement that adds yippee_n1. Fantastic, that looks good. And now CodeGen, of course, does not implement it either. So let's go to the CodeGen, and there we go, it's not implemented. So this is where it actually gets interesting, because here we emit bytecode. And well, we emit an intermediate representation of the bytecode called pretty_op. And pretty_op is just operators or operations, instructions, whatever you want to call it, but they're kind of pretty because you can render them. And this is where the UX library also comes to fruition or whatever the fucking word is. It supports a couple weird things like jumping to labels and declaring labels and adding comments and stuff like that, which are only useful if you then render this into text instead of rendering it into bytecode. So but these are useful, like these are emitted by the bytecode. So at any point you can essentially, I'll show you actually, because it's kind of interesting. Oh, here's all the conversions from and to. So like here's the string format, here's the bytecode format. It's very ugly, but it just works. So in the tests, make sure that it does work. Anyways, so you can see that, for example, label jumps and stuff like that, they cannot actually compile. This is not allowed. Like it's not allowed for this to ever reach that point. And there's this struct called a bytecode. And what we can do with a bytecode is we can essentially say, okay, I want a new label at this current position. So you emit bytecode into it by saying, emitting pretty_op. And then you essentially say, okay, now I want to emit a new label, right? And I want to say the current location is my label. And then later you can set this makes a label, and then you can set the label saying, okay, currently where I am right now, I want this to be my label. And this pushes a fake label. And then what happens with the resolving later, when we generate bytecode, right before we generate bytecode, we go through and we replace all the jump label instructions with real offset jumps, and we calculate the offset sort of on the go by getting the label offset. And that's how we get all these offsets that we see in like this. This is an offset of +2, this is an offset of +2, right? So we get that by first placing labels and then getting rid of the labels. And actually that reminds me that this label instruction is not real, because we don't use the label instruction anymore because it mess up the, where is it? Whatever. The label instruction isn't real. I get rid of it and I forgot to remove the code. But anyways, yeah, there's also some substitution optimization. So for example, if you do load I1 and then add that to a thing, then we make that inc I increment operator. Same with like compare not equals jump false. We then have jump not equals. And this is all intended to be an optimization step, right? Like so this can technically be generated and it'll work, but this is much faster. Anyways, so long yappage, but essentially we need to, we also need to do this. So the function declaration does not declare anything. This allocates stack space. We don't have stack space for those, so that's right. Anyway, so now let's go to the function. So in order to generate a function declaration, we actually sort of want to not emit code at the same location. We want to essentially say, and let me just mock this out. I want ctx dot code dot what do we want to do? We want to emit a function we want to emit a function that contains or like start function maybe, or maybe function builder. And then we do essentially builder.emit blah, blah, blah. And then at the end we do ctx code, or maybe we do like builder finalize. That's my idea, right? builder and pushes it back into the code or something. Because and code, by the way, is just a bytecode struct. So this is the main code. But I think what I want is I want there to be some sort of overarching bytecode struct, which is what this is. But I then want it to have like sub things. And I think the fact that the labels are in here is not a big deal. I think we can just do like effns, right? And then we can do vec, or actually this should be a hash map of string and vec pretty up, essentially. And then I want this to be able to be pushed into. So I almost want this to be another bytecode thing. Then we have to take care of the changed thing, which is a little annoying, but let's just see what happens. Let's just see what happens. These are internal functions, right? So we'll also need call instructions, but not right now. So we'll need a builder. Should we call it the builder? I don't know what we should call it. It's kind of difficult to come up with a nice API for this. But I like the idea that we essentially claim a ownership of the code thing. And hold on one second. Yeah. So I essentially want to say you take a reference to this, and then or would it maybe make sense to like, yeah, it would make more sense to just do a new one. Okay, so hear me out. So I'm thinking new function itself, which returns a mute bytecode. I think that's all we want. And then what this is going to do is going to yeah, that makes sense, I think. So we essentially say self and then this is going to have a name, so this can be a string, I don't care. Oh yeah, this cannot actually exist yet. So self and the insert name bytecode new. And what does insert return? Option. Okay, so let's actually assert that this doesn't exist, because I don't think there's any reason for the function to already exist. Or yeah, well, let's make a way to have function check. So function has function self name stir bool, and then that just returns like contains key, and we're gonna be fine. And then we just assume that this is already, so we assert that as function name, because there's no reason for this to already have that function. Okay, and then we just do that, and that's not right, and that's, well, that's kind of correct. And that should be it. And this is a little inefficient, but like we don't care right now. If it shows up in the profile later, it shows up in the profile. If it doesn't, it doesn't. So if CTX code has function name, I think this is a string, so we will, how do you error from this? Please tell me we can error from this. My God, no, please tell me we can error from this. We cannot error, okay. Then this has to be done earlier. Let's assert here as well. I know it's a bit much to assert it twice, but like, we just want to make sure, right? So let mute bytecode is c2x code a new function name. And I think this should take a str, and then we can just make it to string here. Because that's much easier. Okay, and then stop complaining. Okay, so now we can emit stuff into this bytecode, and it can then later be finalized by something, so we don't care. Oh, but this means that we can have functions within functions, which is not ideal. Like, that's okay, but like, I don't know if we want that. Because I don't think that's how the lookup's gonna work. I guess we can do that for now, and then we can see later if that breaks everything. This is not like a very big code base. It's not a big deal to have to rewrite this later. Almost an hour. Hope you guys are enjoying it. By the way, if you're enjoying it, if you're at this point in the video, you have to subscribe. You have to leave a comment saying "Yippee yeah, I made it," because otherwise, you know, cringe. All right. Fantastic. I'm gonna take a little break to get some water, and I'll be right back. All right, we continue. So, we now just emit normal code, I guess. Well, the first thing is gonna be that we need to figure out, like, okay, we have our arguments, our return values, stuff like that. What does that mean for us, right? Like, what do we even do with that? Do we assume it's already there? Because like, how do function calls work? Because the way I had imagined it is that function calls put stuff on the next stack frame. So a function call generates the next stack frame and then puts stuff on there. But that's actually really stupid slow. So because the arguments exist before the call. So how about we just require the arguments to be, well, they could be the last things in the stack, I guess. Guess they could be, or I mean, a mem copy isn't terribly slow, I guess. If we already allocate, we might as well mem copy the arguments over, but that's a lot. Like, that makes sense for like some things, but for other things, that's gonna be miserable, like larger objects, if we want to pass things by value for some reason. Then we probably just want to pass pointers. And I guess we can do that, right? I guess we can just pass pointers. But that would be a new data type. That kind of sucks. So we could look at the Lua VM, as I said I would do. I don't know if I said that in this recording or in the previous one that failed, but like, because I recorded another intro before this. But I think we're gonna be fine. So I think it's fine to arguments to a function to be pushed to the stack, or get this, new instruction for allocating arguments. That's also a possibility, because I just realized we're not gonna have to worry too much about that, because we can tell the code generator how exactly to generate code for these arguments. So how about we allocate a couple variables, which are called slots. And so, for example, okay, we know we're gonna have 5 arguments, right? So we allocate a couple, where is it? Slots. Where are the slots? Come on, give me a slot. What the fuck? There. Slots allocate, right? We allocate a couple slots, and we can essentially have a function like allocate n slots that have to be at the top of the stack, right? So essentially we say, okay, allocate some slots, that will be at the top of the stack, and that will be essentially part of the next function call thing. And then we have a special instruction at the start of the function declaration that says how many arguments it expects. That could be possible. So it would essentially validate at call time because of the way that it's called, or the call instruction has, we use a couple bytes of the call instruction to do that, but that's kind of, I guess we could limit the amount of things you can pass to a function to 255 and just use 1 byte for it. Essentially saying, hey, you want to pass more than 255 things to a function, you're shit out of luck. That still leaves us 6 bytes for the address, which is more than 4, I guess, which is quite probably more than enough for any kind of code you'll ever be writing in Macha, but it's not beautiful. It's not beautiful. But I think that's what we're gonna do. We're gonna have in the function call how many arguments it has. So essentially we're gonna have like, call hello world, and this is not real. Like this would be some sort of let's do it like this. So this is the address, and then this is the amount of arguments, and this is the address, right? And this would essentially call it with 1 argument, and then before that we would have normal like load I S5 or 6 or whatever, right? And then it would call function 1, function 1, 2, 3, 4 with the argument of like essentially saying, okay, here you get one of the stacks, one of the stack elements. And then what the VM has to do is has to sort of allocate a new stack frame on top of starting at S5. That's the idea. I think that's how we're gonna do it, because otherwise it's gonna be fucking complicated. And I want this to be as simple as possible, because allocating a stack frame should really not do anything until you start having variables and shit. So also we need to do this, count decals. We need to do that for the function declaration, because this essentially tells us how many. So number of declarations is count decals of the body. And I think this is probably not the right, it is the right syntax. Okay, so the function name has n decals, right? Which essentially means that's how much stack it will use. And we can determine this essentially by looking through all the things and essentially counting all the times we do an declaration, or like some other kind of thing. We have some sort of logic here somewhere. Let's see, where is it used? It's used here. Yeah, so this says next index is how many decals we have, because, okay, yeah, so we need to do a little bit of magic here. We need to do this. Let's do that. So this is not contexted slots, because this shouldn't work, right? It shouldn't let us access this. I guess it does. It doesn't matter. Oh yeah, slots. Slots need to be per function too. I guess we have to do a little bit of refactoring then, because this isn't gonna work. I think the bytecode thing has to have the slots. Or we give it a new context altogether. That's a little wild, but I think that might work. I don't know what the context has. What does the context have that we don't have? It has its own const table. No, that's too much. That's too much. So how about we get rid of the slots and we put them in the bytecode? I think that's a good idea because the bytecode really needs to take care of the slots in some way. Not really, but like it's kind of its responsibility because each function has its own slot system. So let's just do it. Let's just do it. Stop yapping and just do it. And we're just going to do this. And slots is not defined here, but that's okay. It's a little bit all over the place. I think we need to clean this up later, but it is what it is. So we then, this entire thing of counting the declarations kind of is a bit shit. Slots is public. Makes it a little awkward, but no, it isn't. How is that private? That's public. Am I crazy? Slots of bytecode is private. No, it's not. It's public. Okay, whatever. Not dealing with that right now. Each of them has their own slots. Because the slot system is really not that bad. I think we could just leave it. Or we could keep it with the general slots and just keep allocating them. But that doesn't make sense because we get a new stack frame, right? The frame, yeah, that doesn't make sense. Next index plus equals decal. So I think we need a notion of like allocate decals or pre-allocate. Itself n some amount. And that's gonna be self slugs next. Oh, the slots needs to be in a different. I'm fucking stupid. Sorry. My bad. I think we should just move the slots out into its own file. There's like no point for this to all be in here. Let's do that. Let's move all the slot shit out. Okay. So now we can import this. And of course, slot has to be, all of this has to be, well, actually, not really. Oh, sorry. First, local use size. Because otherwise this isn't gonna work. And this is some sort of complication where I have to be honest, I don't know if this is gonna make sense, but we're just gonna have to push for that. And when we start making the bytecode, I think we need to already give that to it because I don't think it makes sense to have, yeah, see, we can just counter decals and then give it to the bytecode here. So just, sorry, decals. Because there's really no point in not having this, so. My God, I'm struggling today. Okay, so this is gonna be first local. We can rename these later. I don't think it matters right now. Oh my God. Mic is in front of the thing and I couldn't see my keyboard for a second. I got confused. New first local. Okay. I think we need to restart the language server. Something's wrong with it. Something is wrong. It might have to do with the fact that we don't actually slot type. Okay. Oh yeah, slot. It also wants to slot. Okay. Whoops, my bad. Okay, so yeah, it's used in all these tests, but that's not really my concern right now. Okay. So slots max. Yeah, so then we ask it how much do you have allocated, right? Like that's gonna be what we do. So how much do you have allocated will be a question you can ask the slots. We can essentially say, okay, hey, what's your current allocation count? And that's gonna self and it's just going to return self next index total alloc, because that's essentially how many things you need to allocate in order for this to so this is ctx code slots. What's going on with it? I think I know what's going on. Yeah, there you go. So slots, now it's gonna work, right? Be confusing here, but it's fine. Okay, slots dot total alloc. Whoops. Okay. I think into bytes could also insert that, but maybe right now it's fine. Yeah, I think we need to put this into the. So what this does is essentially it builds the code, the final code, by prepending an allocation at the beginning, because it doesn't mess up any of the jumps, because all the jumps are relative, right? So we essentially say, okay, I want 5 stack variables, and then we start. Yeah, so 1 second. Okay, let's see. What can we do? What can we do? So essentially, we just want instead of having into bytes, well, not instead, but additionally, we want to have generate final bytecode. I don't really care what it's called right now. So this is going to be a vec of UA. And I almost want to make this private because there's no point. Oh, whoops. Where? Okay, there we go. So now let's see what we can do. So we essentially want to do this. Generate final bytecode, or into. So we'll do this. And so the couple things that are interesting here is the fact that slots max now has to be in here. So that's self slots total alloc. And this is bytes. So self into bytes. And then final code. And does extend from slice just take, okay, that's a little annoying. That's a little annoying, yeah. It's fine, whatever. This can be optimized, but it's fine. So into final bytecode now does all of the allocation thing and whatever. That should be fine still, should still work. So final code. All right. Oh, and also we need to resolve labels before we do that. Yeah, and so to do right here. So this actually doesn't make sense. Let's do generate final bytecode, or let's generate bytecode. Because I don't want this to actually do that. I want this to do this because we still need it for the other things that are in there. It's a little confusing that we go from like consuming it to like something else, but it is what it is. So we say generate bytecode that generates the bytecode for the current bytecode, I guess, right? We still have all the functions to worry about though. And they are a little different, right? Because we have to still resolve the labels. I think this is I think the resolve label step is different though. And I think the finalizer for this should also be like, well, we'll have to think about. We'll have to think about. So, I don't think we use with capacity anywhere, so we'll just get rid of it. Bytecode new function. Yeah, so this also needs to have like decal count usize, which is something we can have. It's just we walk the tree and we figure it out. It's not a biggie. Okay, that so sort of fixes all of that. Now we've fucked every single one of these because they now do slots.allocate instead of doing code slots.allocate. And I think that's fine. I think that's a change that I can make pretty quickly by just walking through and replacing this everywhere. It's not the prettiest thing in the world, but like, you know, what is? Except for my wife, of course. Code. Oh, God, I feel like something in Z makes it so if you click on a character, sometimes it doesn't like quite hit it. You know, like what is this? Am I not hitting the character? It's like clicking the wrong one, you know what I mean? So I have to kind of click on the dot, even though I can't click quite on the dot because that's also not right. But annoying that it does that. Slots. Hope to God that this is right. I could do search and replace, but I just don't think that that is the way to do it. So what is this not like? Oh, these are all private. Yeah, I need to fix that. I need to fix that. That's fair. It all needs to not be private, I think. That's very silly for it to be private. It's just a struct. We don't need to worry about. No slot has to. Oh, we'll get to that. Oh, that's it already. Okay, cool. So this is and decals. That works. Fantastic. So now we just need to import no slot. And I think the way we do that is this should be pub. This needs to be public. We need to include that. So use slot, no slot. What else? What other errors do we have? Fucked up the copy paste. Nice. Where else did I fuck up the copy paste? Code slots allocating. Yeah, these are not public. Of course, they must be. They must be public. They are public. Okay, what other errors do we have? I think that's it. Yeah, I think it already figured itself out a little bit. Nice. So all the tests are failing, I think, but that's fine. Let's see if we can still get this to run. Yeah, still runs, which is good. It's just that we run in here. So we essentially want to do the same thing we do with everything else, but on the body, right? So we essentially want to, so the body is a box meta expression. So body code is going to be, what the fuck? Oh yeah, that's a good point. I could just do this. And that would give me the compiled code, but that's not what I want. I don't want the compiled code. I want gen expression. Because I want this because I want what? Oh yeah, the context. It's interesting because we need to make a copy of the context. So let ctx let fn ctx clone. Of course, it's not implemented for ctx. That makes sense. Gen ctx, make that clone debug, and make bytecode also clone debug. And make slots also clone debug, because there's no reason for this not to be clone debug. It's not like they own anything. ctx none. Okay, so the way this works is going to be that we assign. Oh my god, I'm so bad at everything I touch. Okay. Yeah, this is the interesting part, right? So is this not how this works? Yeah, it's not how it works because fuck, okay. So I guess the code has to be a box. Is that how that's gonna work? Does that impact anything? I don't think that impacts anything. Other than that this now needs to be boxed. But I don't want to clone it. So I guess I want to keep these in box 2. I guess that's what I want. And then I want this to be a box. Box new. And I think the fact that it needs to be mutable is a little annoying. Can we not box something mutable? I guess if the box is... I guess this is what we want. I'm just trying to mess around with this to see where I can get, you know? It's really not very interesting, but... Oh. Can we do this? Is there some way to like into this? No? How can I, okay, how can I possibly go from a box of mute bytecode to a box? Do I even want to? Like, what if instead of this, this is what I do? Oh, wow, no. Yeah, this is what I do. So what if instead of that we do this, and then this returns a mutebox bytecode, and then can we not do that? I feel like that should be possible. Um, can compiler fix this? I don't want to deal with this. Like, I just want to have a bytecode thing, and I just want to pass it in. Oh, dude, I'm so stupid. This is fucking stupid. I'm so dumb. I'm so stupid. We're just going to give it a function. Sorry if you've been screaming at your screen the entire time. I'm very slow today, Jesus Christ. I'm very slow because, of course, it's way easier if we just build the bytecode and then give it at the end. Way easier, way better, way less weird. Like, I guess I was just confused by my initial idea of having a builder class of some kind, or struct of some kind, where like we build it up or whatever. And I think I've just now figured out that that's not what I want at all. So at the very end, we want this with the function that consumes it, and then we're good. And this doesn't like it because it's usable removed value. Yeah, I don't care. It's fn_ctx, and this can be inlined. Fantastic. So finally, I figured it out. So now that we have the body code, let's see if it works so far at least. Yes, so far it didn't panic because of that. So, okay, so we do all this, we generate a new thing, and now we generate an expression into the new bytecode thing. And I guess all I now have to do is nothing. Nothing. I don't have to do anything with this. I don't have to do anything with that expression, I think. Oh, no, yeah, I do have to do something with that expression. Because I think what I want to do is I want that expression to return me something. That'll be interesting. So how do we return a value? How do we return a value? I think that'll already be on the stack a space for it. Right, so our stack will have, so we will, let me go back to my link time notes. So this is not really the right place for it, but like, so we do like load I s1, 2. This is argument 1 or argument 0. Then we'll do another one. Oh, let's put them at like 6 and 7 or some shit, right? So these are the arguments. And then we do load is8, or probably here. 5, 2, return value. And we essentially want to encode the fact that this can return something somewhere. And I think the code generator has to do that as well. So how about the bytecode hash map instead of storing string, string, because that seems kind of a good idea. Ish. I don't know. Oh no, it also needs to store the arguments and everything. Okay. So this is a That's called function bytecode. So or how about we call it fn bytecode? And this will just be bytecode for the most part. So, but it also has the amount of arguments, the amount of, well, the return type. So the this is going to be n args, and the return value or return type. There's all the things that we have, right? And the args, I think the args will also be a vec of string. So essentially we want to store most of the things that are contained within in this thing. And now instead of making this, we'll make a, yeah, that's fine. And instead of this, we will make bytecode is function bytecode. And then this actually needs to give these things. So I want the args back string we'll clone it, and I want the return value option string head clone. Is that crazy? I don't think that's that crazy. Yeah, because now we have all the things we need, right? And that makes it kind of easy for this all this shit to work. And well, I mean, we still have to do args and return type and whatever, but like it's not that bad now. And this obviously needs to take a reference to an option because I don't want to copy it until I actually copy it. Okay. So we take the args, the return type, and stuff like that. And that'll tell us essentially how much we want to allocate, right? So count equals blah, gen expression, body code. We don't really want the body code, but I don't know why I still have it. I added it back and I don't remember why. Now what do we do? What do we do? We do that's it, I think. Oh, we want a halt instruction, I reckon. But I think the return is going to I mean, this isn't body code. This is the slot type shit, so we don't need that. If the, what is it called? It's called the body, right? So what if the function context.code dot I can't look into it. So how about new function makes sure that there's a, at the end of it, there is a thing. So if let's do it first. If bytecode code last matches I want this to match a, what's it called? Pretty up return. If that if it's empty, or write code last. I don't think this is gonna work. Simply because I know that we're gonna have multiple return instructions. So if it's empty, we want to terminate it. So we want to say byte, oh, we need to make it mutable. So bytecode emit pretty op return. So also, if at this point let some type red, then I want to panic because that doesn't make any sense. Should be checked before. I think we should check that before. And then we do a normal return. Generate that variant, and that's fine by me. And then we'll have return I, and it'll have an actually, I don't know. Yeah, I think we validate that later. I think we just have one return instruction. And if that doesn't make sense, then so be it. Or bytecode code last listener return. Oh my god. Or I'm so bad at this today. What's going on? Not much. This is what I wanted. So there needs to be at least one return statement at the very end, right? Because the return will actually signal us to return. It's not going to be like, whatever. It's going to be actually like, oh, you need to return. Like, this is going to be the signal. If we run into it, we need to return. Otherwise, we run out of code to run, and it'll be bad. Because the VM doesn't actually do any validation on. I mean, it does do validation on jumps and on stuff like that, but it doesn't do validation on bytecode like program counter increments, because it assumes that every sequence of code is essentially terminated by something that terminates it properly, like a return, a halt, or something. Halts the VM, but like there's other shit that you can put there. And yeah, so we want this. And that should be good. That should deal with that. Now, let's say maybe make function. Let's name it make function, because it sounds a little bit nicer to like make a function, because it actually does stuff, right? It's actually registers the function, and it like checks stuff and whatnot. So that's pretty cool. And yeah, let's see how far we get now. If we now return no slot type void, which is exactly what this expression is. And I think we're, ooh, wait, why? Oh, yeah, makes sense, because we need to implement this everywhere. So, but I'm just gonna let the LLM do it because I cannot be bothered. We still need to think how we're gonna actually do the return, because it's not gonna make much sense otherwise. So opcode return su8. No, we don't have a return opcode, but I'm going to make it. Okay, I'm gonna make it happen. That's fine. And actually I want return to be 91, or No, let's do 90, and then we have call B91 and so on, and we'll get there. Okay, further, we need to implement here, makes sense. This is just like the 3 places you have to implement every single thing. It is what it is. Feel me? VMRS, yeah, so of course the VM has to now deal with that opcode, which is fun because we don't really have it yet, so just leave it as a to-do. Runtime error. Yeah. Okay. Codegen. Yeah, so now the return statement fails. And I think the return statement is going to be interesting because we want to take the is it ridiculous? Is it ridiculous to like load the return statement on top of the stack once we return or something like that? There has to be a way to like return stuff properly. I'm thinking like I'm thinking we load it into the stack and we say, hey, this is a special value. But that's kind of whack too. What else can we do? We can return it into a pre-allocated slot. I think the bytecode would then have to know where the result goes. That's not bad. That's not bad. Let's do that. I think the bytecode knowing having a result slot is not the worst idea. Or maybe a function having a result slot, yeah. So the fact that it doesn't know that it's function bytecode, a little weird, because it cannot access its own args or its own ret or its own anything. We need to sort of tie that together at some point. Let's actually implement call as well, because otherwise I don't think we can continue here properly if we don't have calls. So let's do hello world 2. Let n hello world 2. So this, oh, actually it should be 1 or 0 or 2. 2 is fine, 2 is fine. So this should generate a function call, which it does. No, it does not. Yeah, it does. Function call hello world int 2. Not implemented in Macha codegen. That's the only place it's not implemented right now. The other ones just actually do work already. Wait, what? Oh, no, it does that first. Yeah, never mind. Let's put the call first then, so that we can implement that first. This should be valid because I don't want this to like have issues with that. So, okay, codegen 214. Func calls not implemented. Yeah, that makes sense. Wait, what? What is this? Func call. Oh, that's the actual arguments. Each of them is an expression. Yeah. I remember. Okay. So we will allocate some sort of context code slots allocate args args len. So this is the slots, right? And so we want to implement this. And the way it's going to work is it's essentially just going to call allocate a couple of times. Yeah, that's literally it. So no, that's not literally it. That's fucking retarded. Sorry, that's very dumb. For in, we essentially say args is vec with capacity len, and then we essentially say args push allocate self allocate I think that makes sense. Maybe not. Hmm. No, that doesn't make sense. We don't want that. We want to manually allocate them just to make sure that we actually get them all. We first want to look up the functions. So if we've seen the function before, that would be nice. Otherwise, we can't really do the type checking here. So it'd be nice to go through and do the function calls first. Maybe we can to do resort resort the AST to put function decals first. Well, actually, that doesn't make sense either. So we need like a first pass of some kind. I reckon we need a first pass that essentially says, okay, here you go. Walk through all the functions. All the functions. I guess I want to do two steps here where I essentially allocate each of the functions and do those first, but they can refer to each other, so that doesn't work. So I guess I want to do yeah, I guess I want to do the function declarations first. And I don't want to assert that it doesn't have the thing. Because this will insert it. But this also, okay, this also accepts one. Yeah, we need to think about this. I think that's enough for today. I think next time we can continue more. I think it's been a pretty long, almost 2 hours of nonstop coding. So I think I'll take a little break here and then we'll continue next time. Because I think I need to think about this a little bit and I could also use some comments. So yeah, thank you for watching and have a fantastic day.